We'll talk about 9.3, yes.
Well, I thought this sheet was doing that.
Some of them, well, the equations will go on the sheet. Most of it will go on the sheet except for the examples. All right. So a hyperbola. We get a hyperbola when we cut through the cone in two places. And you have a nice drawing of the hyperbola on your note sheet there. So notice that hyperbolas have two pieces. We have two pieces that kind of look like parabolas. But hyperbolas, though they behave, their characteristics are more like an ellipse that's been kind of turned inside out, sort of. So when we talk about our equations, the information that we talked about, the A, the B, the C, tell us the same information for hyperbolas as they do for ellipses. But the arrangement of the A, B, and C are slightly different for hyperbolas than ellipses, so that their relationship is a little bit different. Well, let's start with the locus definition. Hyperbola is the locus of points in the plane. So there's a little space to the right of the picture on the top of your sheet there that you could write this in. So that the difference in the distance from two fixed points, the foci, is constant. So contrast that with the ellipse. With the ellipse, we said the sum of the distances was constant. Here we're saying the difference is constant. So if I draw a little picture, here is an ellipse, a hyperbola, and my foci are inside the curvy part of the hyperbola. So what we're saying here is if we have a point on the hyperbola and we draw the distance from this focus and the distance from that focus, and I call this distance D1 and this distance D2. What the locus definition is telling us is that D1 minus D2 is constant. For any point on the hyperbola, if we subtract the two distances from each other, we get the same number, no matter what. So all the other information about hyperbola is really going to be very, very similar to the information about an ellipse. We have our hyperbola is going to have a focus. They're going to have a vertex. They're going to have a co-vertex. We'll give it a slightly different name. And our relationships are going to be really the same. And the procedure that we use to solve problems is really going to be the same. So let's talk about our standard equation. We'll start with a horizontal hyperbola. So this is going to go on your sheet. So let me grab my picture here, and we'll fill this in. There's this. There we go. All right, so there's the part of on the left of your sheet. I'm going to label a few things here. So our hyperbola has a vertex. So each of those are vertices. Our foci, so there's a focus. This is going to be called the axis or the transverse axis. Axis or transverse axis is either one is fine, so I'm just going to write. So our transverse axis or axis is horizontal here. This other axis we call the conjugate axis. And we also have these points that aren't on the hyperbola, but they're going to be related to something else that has to do with the hyperbola, that we call the conjugate vertex. And this would be a conjugate vertex down here. On the ellipse, we call those the co-vertices. The distance, oh, and this is our center. The distance from the center to the vertex, I'm going to highlight that there, is A, just like in a ellipse. The distance from the center to the conjugate vertex, that distance is B. The distance from the center to the focus is C. And I'm going to draw in the hypotenuse of this nice triangle here. So I'm going to join the conjugate vertex and the vertex. That distance is also C. So we have a nice little right triangle in my hyperbola, just like I had a right triangle in the ellipse. So for a hyperbola, C is always greater than A. The distance from the center to the focus is larger than the distance from the center to the vertex, always. And from this little right triangle here, we have that C squared equals A squared plus B squared. So this is the difference in the relationship between A, B, and C in a hyperbola and an ellipse. In an ellipse, we had A squared equals B squared plus C squared. A was always bigger in an ellipse. All right, so our equation, x minus h squared over a squared minus, we have minus because we said the difference in the distances was constant. Y minus k squared over b squared equals 1. So this looks exactly like the equation of an ellipse, except we have a minus sign instead of a plus sign.
Should it over b squared or over b?
Oh, this should be b squared, sorry. The way that we can tell that this is a horizontal hyperbola is the x part is positive. The x part is positive. That tells us our axis is along or parallel to the x-axis. For a hyperbola, a squared is always under the positive part. All right, so our center is at HK, just like we'd expect. The transverse vertices are right and left from the center. So to find our transverse vertices, A tells us how far to go to get to the vertex. So we're going to go H plus or minus A, K. We're going to go right and left from the center. The conjugate vertices. B tells us how far to go from the center to get to the conjugate vertices. So we're going to go up and down. So that's going to be H, K plus or minus B. I'm going to jump down here to the foci. C tells us how far to go to get from the center to the focus. And we're going to go left and right. So that's going to be H plus or minus C, K. So that all that information is exactly like it was for an ellipse. The eccentricity is C over A. And I'm going to write over here eccentricity, E is C over A. For a hyperbola, our eccentricity is greater than 1. If E is close to 1, the hyperbola is more closed. So our hyperbola would look like this. If E is large, so much, much bigger than 1, our hyperbola is more flat. So it would look more like this. Well, and we also see from the picture that our hyperbolas have asymptotes. So we can write the equation of the asymptotes. The asymptotes go through the center. So the point HK is a point on the asymptotes. So we can write the asymptotes in point slope form. Y minus K, just like this, equals the slope of the asymptote. That's what the conjugate vertex tells us. The rise here is B, and the run is A. So the slope is going to be plus or minus, to get both asymptotes, B over A, X minus H. The rise is B, the run is A. All right, so very, very much like a ellipse. All right, questions? So we'll talk about the vertical axis, and really the information is the same, except we're going up and down where we went left and right. We're switching the direction that we go to find our piece of information. So it's very much the same as we talked about with the parabola and with the ellipse, and very similar to this. So let's jump over there. Here's my vertical hyperbola. All right, for a vertical hyperbola, C is still bigger than A, always for a hyperbola. C is still the distance from the center to the focus. A is the distance from the center to the vertex. B is the distance from the center to the conjugate vertex. And I'm going to draw in this nice hypotenuse here. That length is also C. So we still have c squared equals a squared plus b squared. The way that we can tell that the vertical, this hyperbola is vertical, our equation, y minus k squared over a squared minus x minus h squared over b squared equals 1. The y part is positive for a vertical hyperbola. A is always under the positive part. A squared is always under the positive part. The center is at HK. The transverse vertices. Well, A tells us how far to go to get to the vertices. This time we're going up and down. So it's going to be HK plus or minus A. The conjugate vertices. B tells us how far to go to get to the conjugate vertices. This time we're going left and right. H plus or minus B K. The foci. C tells us how far to go from the center to get to the foci. We're going up and down. So that's going to be H K plus or minus C. Eccentricity, still C over A. The asymptotes still go through the center. So I have y minus k equals, well, this time the rise is A and the run is B. So my slope is going to be plus or minus A over B, x minus h. So the relationship between A and B tells us how closed or how open the hyperbola is. B isn't a point, the conjugate vertices. We don't get a point actually on the hyperbola, but it's related to how closed or open it is. All right, questions there? Yes?
Is the eccentricity also always greater than 1
For a hyperbola, yes. Because C is always bigger than A. So the eccentricity is going to be bigger than 1. And in a ellipse, C is smaller than A because this focus is inside. All right, let's fill in the rest of the information on your note sheet. For both types, over on the right, A is always under the positive part. Underneath it says you can tell whether it is a horizontal or vertical hyperbola based on which part is positive. X is positive for a horizontal, Y is positive for a vertical. Yes? The distances down at the bottom from the center to the transverse vertex is A for both types. The center to the conjugate vertices, B for both types.
Can you repeat that last two things you said?
Distances, center to the vertex is A. Center to the conjugate vertex is B. Center to the focus is C.
Both types?
Both types. All right. So the type of questions that you're going to be asked with hyperbolas, very similar to the types of questions you're asked about ellipses, very similar to the types of questions you're asked about parabolas. It's the same question asked in different ways. You're given various pieces of this information, and you use what you know to find other pieces of information. So let's look at a couple of examples. We want to find center, vertices, foci, asymptotes. Of 4y squared minus 9x squared equals 36. How can we tell this is a hyperbola? A negative sign. If it were a plus, we'd have the exact same example we did yesterday with the ellipse. So what's our first step here? Divide by 3. We want it in standard form. There's a 9 and a 4. So when we put it in standard form, we get y squared over 9 minus x squared over 4 equals 1. There's our standard form. And now we have everything. Is this vertical or horizontal?
Vertical.
This tells us it's vertical. What does this tell us? A equals 3. This tells us B equals 2. Where's our center? Center's at 0, 0. I'm going to draw a little sketch over here just so we can see how we would sketch this if we needed to sketch it. Our center's at 0, 0. It's vertical, so we're going to go up and down a units to get to the vertices. So the vertices are 0 plus or minus 3. So there would be a vertex at 3, 0. And here would be a vertex at minus 3, 0. What else do we need? The foci. We know that c squared equals a squared plus b squared. So c squared is 9 plus 4, 13. So c is the square root of 13. So our foci, we're going to go up and down from the center to get to the foci. And I wrote these backwards, didn't I? 0, 3, and 0, negative 3. So our foci are going to be at 0 plus or minus square root of 13. Is the square root of 13 bigger than 3?
Yes.
Yes, because 3 squared is 9. So my foci are going to be out here beyond the vertices. And if I wanted to sketch this, I would sketch my transverse or my conjugate vertices. I'm going to go left and right. So that's going to be plus or minus 2, 0. So my conjugate vertices are going to be here. And minus 2, 0. So to sketch a graph, what you're going to do is sketch a little box through the conjugate vertices and the vertices, like so. Your asymptotes go through the center and go through the corners of that box. That's how we get the slope of the asymptotes. So those would be my asymptotes. And then I would sketch the hyperbola like so.
Do we have to write the graph for these problems?
Some of them will ask you to graph. I just wanted to give you an example of, in order to make your graph accurate, you want to sketch the little box and draw your asymptotes. And my asymptotes, it would ask for the asymptotes. My asymptotes would be y equals plus or minus. The rise here is a, and the run is b. So my asymptotes would be y equals plus or minus 3/2 x. All right, questions? All right, let's look at a slightly different type of problem. We want the equation, standard equation. Of the hyperbola with transverse axis length 4 and foci of plus or minus 3, 0. So what I'm going to suggest for this one is start to sketch a little graph. My foci are at 3, 0 and negative 3, 0. So is this going to be vertical or horizontal? Horizontal. The foci are on the transverse axis, so we know it's horizontal. Where's the center? 0, 0. It's halfway between the two foci. So our center is at 0, 0. So we know that the equation is going to be x squared over a squared minus y squared over b squared equals 1. Well, what does this transverse axis length 4 tell us? A equals 2. So the transverse axis is from the vertex to the vertex. So A equals 2. What does this tell us? C equals 3. So A squared is going to be 4. So that's going to be 4. And we can figure out that we know that C squared equals A squared plus B squared. So B squared is 5. 9 minus 4. I'll write it. You could write 5 squared. I'll write 25. And there's my equation.
No, b squared is 5.
Oh, B squared is 5. There we go. Thank you. All right, questions? Now, one thing to be careful of with hyperbolas. With hyperbolas, notice here that B is bigger than A. For hyperbolas, that's okay. B and A for hyperbolas tell us about the slope of the asymptotes. C has to be larger in hyperbolas, always. All right, let's look at one more. This one should be an old friend by now. We want to sketch the graph of 4x squared minus 9y squared minus 24x minus 72y minus 72 equals 0. This is good. This is a sign of affection. So what do we do here? Complete the square twice. All right, so let's group the x parts. 4x squared minus 24x minus 9y squared minus 72y, and I'm going to put the 72 over here on the right. Factor out these leading coefficients, and we'll complete the square as we go. So we divide that by 2, we get 3, and this is going to be 72. And we need to remember that we're multiplying here, so we have to add 36. For this one, I'm going to factor out the negative 9, so I need to be a little careful. This is going to be a plus 8y. And when we complete the square, divide that by 2, square it. And here I need to be careful because I'm distributing the negative 9 times 16. So on the left-hand side here, I have negative 144. So I need to subtract 144 from the other side. Now we can do this. 4x minus 3 squared minus 9, y plus 4 squared equals negative 36. And here we need to be careful again. We don't want to jump the gun and say this is a horizontal hyperbola, because we need it in standard form, so I'm going to divide by negative 36. When I do that, I get y plus 4 squared over 4 minus x minus 3 squared over 9 equals 1. All right, now we're ready to start getting the information for our graph. So our center is at 3, negative 4. A equals 2. B equals 3. And this is going to be vertical. So I'm going to do my sketch over here, my little sketch. So my center is at 3, negative 4. I'm going to go up and down 2 units from the center to get to my vertices. So this is going to be at 3, negative 2. And 3, negative 6. So for my vertices. And I'm going to sketch my conjugate vertices so I can get my slope of my asymptotes. So I'm going to go left and right 3 units. So this would be at 6, negative 4. And 0, negative 4. So I'm going to make a little box here between all my vertices. My asymptotes are going to go through the center and through the corners of that box. So there would be my asymptotes. And my hyperbola is going to go from the vertex, go along the asymptotes. So we can see this is a pretty flat hyperbola. Yes.
If we're taking a test or quiz or something, do you want us to plug in points?
No. For a hyperbola, it's enough to get the vertices and then the asymptotes. And that's going to be enough information to make a relatively accurate sketch. And for an ellipse, you just need the vertices and the co-vertices. All right, questions there? What time? Okay, we're doing good. All right, the last piece of information. I will show you on block day. I have a nice contraption here for constructing a hyperbola on the board. And I'll talk about the reflective properties of the hyperbolas on block day. But I promised that I would tell you how to figure out that this is a hyperbola without doing a bunch of extra work. So we need to talk about general conics. And this is very similar to general General calculus, this is not about a war hero. All right. General, yeah. All right. Any equation that looks like this is going to be some kind of conic section where A, B, C, D, E, and F are some numbers. We can tell what kind it's going to be by looking at A and C. The number in front of the x squared and the number in front of the y squared. If A equals C, the number in front of the x squared and the number in front of the y squared are the same, it's going to be a circle. If A times C equals 0, it's going to be a parabola. And what this means is you only have an x squared or a y squared, but not both. So you're missing an x squared or a y squared. So you only have one squared thing. That's going to be a parabola. If A times C is positive, you're going to have an ellipse. And that means that both are the same sign. Yes?
Is it greater than 1 or greater than 0 for positive AC?
Oh, thank you. Greater than 0. Greater than 1 would work, but you'd miss some of them.
Yeah.
And if AC is negative, you're going to have a hyperbola. That means 1 is negative. So you're going to have a positive x squared, a negative y squared, or a positive y squared, negative x squared. So if you see a problem that says classify the conic section, you're just looking at A and C and deciding what kind of conic section it is. You don't have, you could complete the square to figure out what it is, but that's way more work than you need to do in this case. And we won't do anything with it really, but if B is not 0, so if you have a term where you have an x times a y, the conic is rotated. So it's not going to be horizontal or vertical, it's going to be rotated in some way. And those get way more complicated.
Are we going to learn about that this meeting?
No.
Okay.
But just so you know.
Thanks.
Well, we already know one of these. Well, let me give you an example. What is y equals 1 over x? What does a graph of that look like?
It's rotated.
Isn't it like this? I can write this as x times y equals 1. This is a rotated hyperbola. The axis is here instead of here. So we already know about one rotated conic section. All right. Right under the wire.